My dear friends, welcome to Rajashekhar classes on Applied Data Science with Python. This is lecture number 518. In this lecture, we will try to understand maxima and minima. Since we have gone through some basics of calculus or basics of differentiation, let's understand what is maxima and what is minima. Imagine if I have function like this. In this function, let me assume this is my x and this is my f of x. This is the if you observe carefully this function, what is this? What is this point? This is the minimum value that f of x takes, isn't it? In similar manner, this is the maximum value that f of x takes. One thing that you will notice here, both at maxima and minima. Just observe this point carefully. Both at maxima means here, both at maxima and minima. If you look at the slope, look at the slope at a minima. Look at the slope here. At minima, similarly, slope at maxima. At minima and maxima, the slope is 0. This is important. At minima and maxima, what is your slope value? 0. Here also, your slope equal to 0. Let's take a simple function. Let me assume I have a function like this, x square minus 3x plus 2. Let's assume this is my f of x equal to x square minus 3x plus 2. If I want to find maxima or minima, so now what can I do? I know that at maxima and minima, your slope equal to 0. Slope is nothing but df by dx. This is the slope. Whether it is maxima or minima, this slope is 0. What is slope? Slope is df by dx. What is d by dx of x power n? D by dx of x power n is n into x to the power of n minus 1. For this, I am finding df by dx. X square means what? 2 into x to the power of 2 minus 1, that is 2x. Differentiation of 3x is 3. Differentiation of constant is 0. Therefore, you will get df by dx is 2x minus 3. For maxima or minima, slope equal 0. Therefore, 2x minus 3 equal 0. Therefore, at x equal to 3 by 2, slope is 0. Isn't it? This is, I can say at x equal 3 by 2, what did we learn? At x equal 3 by 2, slope equal to 0. Now, the next immediate question is it a maxima or minima? Isn't it? This is immediate question. This is important. At x equal 3 by 2, will you get maxima? Is it a maximum value or minimum value? Is it not valid question? Yes, it's a valid question. There are multiple techniques to do it. The simplest one is, if I evaluate this function f of x at x equal 3 by 2, that is 1.5. If I calculate this value, what am I getting here? I am getting minus 0.25. I will take a value close to 1.5. Let it be number 1. Let it be 1. If I take a value f of 1, this 1 is close to 1.5. What are you getting here? F of 1 equal to 0. What does it mean? So, I notice that f of 1.5 is less than f of 1, which implies 1.5 cannot be maxima, isn't it? You won't get maximum value at 1.5 because there is some other value of x which is, so for some other value of x for which you are getting greater value. Therefore, I can say 0 is, what is this? 0 is greater than minus 0.25, isn't it? So, 1.5 function will not get maximum at 1.5, isn't it? So, I can conclude that we have minima. We can conclude that we have minima at x equal to 1.5. Is it not? Yes. So one of the simplest way to determine whether it is maxima or minima. Next important thing is there will be some function which do not have maxima. For example, take a function, let y equal to x square. This has minima at origin. Just see, this function has minima at origin, but there is no maxima, because as x increases, just see, as x increases, your as x, because as x increases, y continuously increasing. Just see, as x increases, your y is continuously increased. It never stops. Similarly, as x decreases in the negative side, it continuously, is it not increasing? Yes. Is so this function has no maxima. It has only minima. It has minima at x equal to 0. Similarly, let's take other function. Let's take a function like this. This function, what about this function? This function has maxima at x equal to 0, isn't it? It has maxima here. Maxima at x equal to 0. That's what this function has, maxima at x equal to 0. It has no minima, because it's keep going like this. Yes, it's keep going like this. It has no minima, isn't it? Yes. So it's possible that you may or may not have minima and maxima. So let's take other function. Imagine if I have a function like this. So let's say I have a function like this. Now this function has no maxima and no minima. This is important. It's possible that a function may not have maxima, may not have minima, because what's happening here, because it's keep going to plus infinity. This part, it's keep going to plus infinity. What about this? This is keep going to minus infinity. Going to minus infinity. Even this case is, in this case, there is no maxima, there is no minima. Even this case is possible. It's not necessarily that every function has minima or maxima. The minimum or maximum. There is other case here. Other case here is the function having two minima, or I can say multiple minima. There is other case here. Other case here is that function having two minima. Just observe this one. Suppose this is my function. Let me assume this is my function f of x. Let me say this is my function f of x. This function has two minima. If you notice, just see, here I have one minima. Here also. Why? Because slope is 0 here. Here what is slope? Slope is 0. Here also your slope equal to 0, isn't it? This function has two minima. If you notice, this is the what is this? This is the minima. This is the minima. Why it is the minima? This is the minima because slope is 0. There is other minima here. This is also minima. There is other, because slope here also slope equal to 0. If you look at corresponding points in the vicinity of all these points, or in the vicinity of all these points have greater value than this, isn't it? This is, I can say, this is minimum 1. This is minimum 1, isn't it? This is minimum 1. So if you have two minimums, this is minimum 2. Here you have two minimums. So it's possible that a function has multiple minima and multiple maxima. So that's possible, isn't it? These are two in similar manner. In similar manner, you can have, just see, this is minimum 1, minimum 2. In similar manner, a function has multiple minima case and multiple maxima case. Just see, in similar manner, you can have two maxima. Which one is two maxima? This is first maxima, and this is first maxima. This is second maxima. You can have two maxima, isn't it? This is called local. This is called local maxima because it is local maximum, because with respect to the locality, and with respect to the neighborhood of these points, with respect to the locality, with respect to neighborhood of these points, if you look at the neighborhoods in this neighborhood, this is the maximum point, isn't it? Whereas here also you have maxima. That maxima, this point is called global maxima, because among all the maxima, among all the maxima, this one is, I have two maxima. Let me say this is first maxima. Let me say this is maxima 1. Let me say this is maxima 2, isn't it? Amongst all the maxima, which one? This one. Yes, amongst all the maxima, this is the lowest, isn't it? So it's possible that this is the lowest, means this is local maxima, isn't it? So it's possible that a function have multiple local maxima. It is always have one global maxima, isn't it? Here you may have multiple local maximas, but you must have one global maxima. In similar manner, you can have multiple local minimas, but you must have only one global minima. Maximum of all the maxima. What is the global maxima? I can say global maxima is maximum of all the maximum is global maxima. That's it. Here I have maxima. Here also I have maxima. Maximum of all maxima, this is maximum of all maxima. If even I can have multiple maximums, in which highest one is known as global maxima. For example, this one is local maxima, isn't it? This one is global. This one is global maxima. This one is local maxima. So it's possible to have multiple maxima and minima. Anything that is not a global minima is called local minima, because in its neighborhood it is the smallest value, isn't it? What is this? This one. If you observe this one, I have here also minima, here also minima. Which one is lowest one? This one is. This is global minima, isn't it? In its neighborhood. I can say in its neighborhood. If you observe this one, in the neighborhood of M1, this is minimum value, isn't it? But here it is minimum value in its neighborhood. Which one is lowest? This one is lowest. Therefore, it is known as global minima, isn't it? So we have seen a simple example here to find minima, isn't it? Now let's take slightly complicated example, slightly more complicated. Just imagine my f of x equal to log of 1 plus exp of ax. This looks like something like logistic loss. It looks like logistic loss, isn't it? In logistic loss, instead of ax, in the case of logistic loss, instead of ax, we used to write yi into w transpose x, isn't it? Let's assume a is a constant here. Now, if I want to perform, I want to find minima and maxima of this function f of x. So, in earlier case means f of x equal to x square minus 3x by 2. What we did, we found very easily by just saying f dash of x equal to x minus 3. We solved 2x minus 3 equal to 0. By solving this equation, we got it very easily. It is not always that easy. For example, if you take this f of x equal to log of 1 plus exp of ax, if I do df by dx, what is the differentiation of log x? D by dx of log x means what? It's a 1 by x. Therefore, 1 by this I am writing. I am differentiating again. Differentiating 1 is 0. exp of x differentiation is exp of x. Again, ax differentiation is a. Therefore, what you are getting? You are getting a into exp of ax by 1 plus exp of x. In similar to 2x minus 3 equals 0. Previously we solved 2x minus 3 equals 0. It's trivial, but in this case, solving this, which one? Solving a into exp of x by 1 plus exp of ax equal to 0. This is not trivial. Sometimes it is very, very hard. In some cases, it is very, very hard to solve, isn't it? It's very, very hard to solve. So if you want to find minima and maxima, just trying to solve df by dx equal to 0, isn't it? Solving df by dx may not always be the best way. It may not always be the best way, especially complex functions like log of 1 plus exp of ax. So we will see some techniques, some computational techniques to find minima and maxima in my next lecture. Technique is called gradient descent, which is a computer algorithm to find maxima and minima without having to solve this equation df by dx equals 0. That's very, very important, because sometimes it's very, very hard to solve df by dx equal to 0. In such cases, we will use an iterative algorithm that I will discuss in my next lecture. Maxima and minima has got so many applications, just not in machine learning, in physics, in business. There are tons and tons of applications for finding maxima and minima. Machine learning is a small area where we use maxima and minima. In my next lecture, I will discuss about a concept related to vector calculus, that is grad. We will try to understand grad so that it will be helpful for understanding algorithms like gradient descent algorithm. Thank you very much.